Так хорошо, это размножает сущности.
Так, это мы сделали. Запись надо выключить. Ладно, давайте запись включим. Так.
Может, ты что, будет любой спросить через час, можно жениху, а может, она его наберет, перезвонил, хороший смысл, нормально.
Я что-то не понимаю, что происходит. Я поделился или нет? Я нажал вроде поделиться. Поделиться.
Так, ты должен выбрать экран.
Нет.
Должен. Вот.
Вот. Нет.
Фу. Так.
Вот, экран уже выбрал.
Вот это.
Да
Вот.
нет.
И теперь ты нажимаешь поделиться. И только теперь ты поделился, по-моему.
Ладно, нет. Оно работает по-разному.
Ну, там Михаил подключился.
Миша, вы видите наш экран?
Презентацию.
Да, я вижу ваш экран.
Презентация видна сейчас, да?
Релятивистик,
Да,
sorry.
отлично. Все, значит, мы правильно сделали.
Но
Да.
тут немножко вот, еще лучше.
Почему так плохо?
Вот видишь, что ты сделал?
Сделал.
Тут обычно есть тот, кто задает вопрос, виден, а ты сделал его невидимым.
Блин, ну Вова, я не знаю. Сделай по-другому.
Окей. Я последний. Let's start today. We are glad to see here and to know something new about plasmon-polaritons from Ivan Andreev, who is senior scientist or just scientist. Okay, senior scientist.
It's not important
Institute of
for
Solid
the
State
sake
Physics,
of our
Russian
seminar
Academy of
today.
Science. Okay, floor is yours.
Okay, thank you. Vladimir kindly invited me to give this talk today. So I will speak about some experiments with plasmons in two-dimensional electron systems. All experiments in this talk was made on gallium arsenide quantum wells, two-dimensional electron systems and high-mobility gallium arsenide quantum wells with some kind of back reflector or back gate, so metallic layer, near two-dimensional electron system. Okay. How to? Okay, it works. So I will start with a brief introduction about two-dimensional plasmonics and retardation effect for two-dimensional plasmons. When I will discuss the realization of strong plasmon-photon interaction in two-dimensional electron system with screen and backgate, discuss some about so-called transverse plasmon-polaritons and show you an experimental implementation of Purcell effect for classical macroscopic oscillator, namely 2D plasmon in 2D electron system. As you may know, in two-dimensional electron system, plasma waves strongly differ from plasma waves in 3D. Because the system is two-dimensional, but its electromagnetic field is three-dimensional, it strongly modifies the dispersion law of 2D plasmons. Unlike 3D case, frequency of two-dimensional plasmons strongly depends on wave vector Q in a square root law. And also such a system, 3D plasma, 2D plasmon and two-dimensional electron system is strongly influenced by the electric environment of such a system. It feels dielectrics near the system or screening, metallic gaze. And the eigenfrequencies of 2D plasmons in typical 2D systems like quantum wells or graphene is in microwave or terahertz range, which
I'm always forgetting this expression. It predicts ultra velocities, group velocities above the speed of light at 0 Qs, right?
This is a very important question. So this equation for 2D dispersion law is obtained in purely electrostatic approximation.
Quasi-static.
Yes. Okay, quasi-static approximation. And of course, it could not be valid in small q region, and I will discuss it just 2 slides later. Okay, so motivation of the interest for 2D plasmonics concerned with rather natural goal to use 2D plasmonics as a link between electronics and photonics. On one side, 2D plasmons and 2D electron systems could be controlled electrically. For example, you may make some kind of gate and tune the electron density into the dimensional electron systems and move and tune plasmon eigenfrequencies. And since its frequencies of plasmons lies within microwave and sub-terahertz,
Don't worry, that's not
okay. Lies within sub-terahertz range, so it's natural to use plasmon resonances into the electron systems to make some kind of devices like detectors in sub-terahertz range, or some kind of modulators, maybe phase shifters, and so on, and to employ such devices, for example, in high-speed wireless communication or imaging and this frequency range and so on. But it's not important for our talk. Okay. Yes, how to go back? Okay. As we can see, the square root dispersion law for 2D plasmons it could not be valid in small wave vector region, because from this quasi-static dispersion law follows that plasmons with small q should have a group velocity exceeding the speed of light, which couldn't be. Okay, so when the dispersion comes close to the light cone, it obviously should be modified This is experiment for unscreened two-dimensional electron disks. Yes. And the experiment shows that plasmon-photon interaction modifies the dispersion and the polaritonic effects give us combined more complicated dispersion, which is more photonic in small Q range and more plasmonic in short wavelength limit. So when a quasi-static approximation is valid, and to quantitatively characterize, to quantify the strength of plasmon-photon interaction. In this case, typically we use dimensionless, so-called dimensionless retardation parameter A, which is a ratio of plasmon frequency calculated in quasi-static approximation to the frequency of light with the same wave vector. And typically we can the light in the semiconductor substrate on which our two-dimensional system is placed.
Excuse me, can I ask a question? What is the difference between this quasi-static approximation and plasmon-pole approximation?
But what do you call plasmon?
Because for plasmons, I mean, static means kind of Thomas Fermi.
No, quasi-static is solution
of say about plasmon-pole.
Continuity equation. That's all. But poles of polarization function is the same approximation.
Okay.
Okay, so let's continue. And in unscreened two-dimensional electron system, it's quite easy to achieve the strong retardation regime when the parameter A is about unity, and the polaritonic effect strongly modifies the dispersion and magnetodispersion of 2D plasmons, unscreened with no metallic layers, which provide no electrostatic screening.
And this is what materials? Gallium arsenide?
The experiment, yes, gallium arsenide. Yeah.
Doped, right? It's doped with.
It's quantum valence heterostructure, yes.
And there is a doping.
Yes, yes, there is a doping layer. But you have no conductivity over the donor impurities. So this donor layer does not screen the plasmon field. Okay, so here is some experiments for unscreened two-dimensional electron systems from the work of Igor Kukushkin in 2003. And when they are comparing, okay, it's performed on disks with various diameters and electron densities. And then strong retardation regime, the magnetodispersion of plasmons in disk drastically change. First of all, plasma frequency in zero field is damped. In quasi-static approximation, it should be here when the arrow marks, but in the experiment it is damped about 1.4 times. And the magnetodispersion in strong magnetic fields, instead of tending approximately to the cyclotron resonance, tries to intersect cyclotron resonance and demonstrates such the negative magnetodispersion regions. Strong radiative decay of such modes in the regime of strong retardation leads to a crossover between different magnetoplasma harmonics and complicated to study of magnetodispersion. So for unscreened two-dimensional electron system, strong retardation regime is well studied before. But what about the systems with some kind of metallic gates? Which system, such system is of particular interest because presence of gate near two-dimensional electron system allows us to easily tune the electron density. And in this work, I will show you some experimental results on the samples, which consist of some 2D measure. It could be disk, or it could be very large square, taking the full area of the structure. Lying on semiconductor substrate, actually gallium arsenide, substrate with a back reflector on the opposite side of the substrate. Okay. First part of my work is devoted to realization of screen plasmons with a strong interaction. In the systems with a gate or back gate, screening interaction with electrostatic image of charges into the electron system leads to strong modification of dispersion law. The dispersion of screen plasmons becomes linear. So with the velocity, which depends on the distance to the gate or back gate, in our case, it would be substrate thickness. And this approximation valid then gouache is much less than unity. And typically, to achieve the limit of the strong retardation, you need that velocity of plasmon into the electron system should be close to the velocity of light, of course. But in common to the electron systems with gates, velocity of screen plasmons is about 10 to 6 meters per second, and the retardation parameter is very small. And the retardation effect or polaritonic effect do not play a significant role. But we achieve the regime of strong retardation in case of screening by simultaneous increase of the sample lateral size, which defines the wave vector, distance to the backgate, and the electron density. So the plasmon velocity due to increase of electron density and distance to backgate tends to the light velocity, and since the lateral size is increased, Q is still very small, and the condition of strong screening is somehow maintained. Not perfectly, but somehow. So our samples used in this work is prepared from gallium arsenide heterostructure with quantum well. Typical electron density and mobility is given here. And in this part of my talk, I will show you the results on disks with diameter from 3 to 10 millimeter on a substrate from 140 to 640 microns. To perform the experiments, we employ the optical detecting technique of microwave absorption, which is very suitable for gallium arsenide. So we illuminate our 2D system continuously by near infrared laser with 780 nanometer wavelength. This laser induce electrons and holes. And the hole density in quantum well is quasi-stationary, quasi-static. Okay, and the 2D electrons recombinate with holes, and we measure the spectra of recombinant photoluminescence signal, and the spectral intensity or frequency is determined by the probability of the recombination, density of states for the electrons and conduction band, for holes in the valence band, and the distribution function of electrons and holes. Distribution function of the electrons is Fermi-like, and the distribution function for holes is Boltzmann-like. So the shape of the recombinant luminescence spectrum strongly feels the temperature of system of 2D holes, namely. When we illuminate the system by microwave radiation, we resonantly excite the plasmon. The system heats, electrons thermalize with holes. The temperature of 2D holes changes, and the luminescence spectrum slightly changes shape. So by measuring and integrating the differential shape with and without microwave radiation, we obtain a quantitative measure of microwave absorption in the system, actually heating of the system, in arbitrary units. And we actually measure the spectrum of microwave absorption versus magnetic field for various frequencies of microwave excitation of the sample. Maybe a bit complicated.
Can you explain once more? So you use just interband optical excitation.
Yes.
Look for its optical recombination.
Yes.
And in the same time, you want to see some plasmonic effects, right?
Yes,
And
actually,
the link between these two.
they use optical excitation as a thermometer. We measure relative overheating of the system by optical technique. And the reason of this overheating is the resonant excitation of plasmons, which absorb microwave energy, which dissipates and heats the system. So we simultaneously excite the plasmon by microwave generator and excite the optical transition by the near-infrared laser interband transition.
It's quite involved.
Okay. Here are some figures for microwave absorption in a disk. Okay. Here is not parameters. Okay, it's should be, as far as I remember, a 4 mm disk with 7.5 to 10 to 11 to the centimeter minus 2 electron density. Okay, and in this sample, we see that actually two observations. First of all, if we calculate plasma frequency in a quasi-static approximation for such screen disk, in taking into account no retardation, so this plasma frequency for this sample should be about 18 GHz, and the experiment is 10 GHz, so the plasma frequency is significantly damped, which allows us to suppose some manifestation of retardation effects. And actually the magnetodispersion in disks, which should have this shape due to twofold degeneracy of the modes and the zero magnetic field. Okay, it's not tend asymptotically to the cyclotron frequency and tend to something else. So its behavior and strong magnetic fields is also renormalized.
Does this happen only in the region when your parameter A for this sample for the samples is large, or this happens for independently on retardation parameter?
It strongly depends on retardation parameter and
no, I mean in case of small retardation effects.
In case of small retardation, effects, the plasma frequency will be at quasi-static value almost exactly, and in strong magnetic field, it will tend asymptotically to cyclotron frequency, for sure. So, and our colleagues, mostly this work is based on advice given us by our colleague Andreev from Kotelnikov Institute. So obtain this result that for screen disk, in case of strong retardation, the dispersion equation has this form where alpha is such a parameter, and it coincides with dispersion relation in absence of retardation if they introduce such proper renormalization of dimensionless plasma and cyclotron frequencies. And returning to the parameters which we directly could measure via experiment, this renormalization takes this form. So the renormalized plasma frequency given by this equation, and cyclotron frequency also renormalizes. And I would like to notice that this term, Vp squared epsilon over c squared, is just a squared retardation parameter. So the strong retardation actually renormalized the plasma and cyclotron frequency. And it's kind of speculation, but it could be described by considering it as a renormalization of the effective mass. Actually, I suppose that no mass is renormalized, but we just have some kind of plasmon-photon interaction, which gives us such a normalization, which is always combined with mass in our equations.
So EM star is effective mass of single electron
Yeah.
in two-dimensional.
Yes, yes, it's effective mass for 2D electron. And for example, we may tune the substrate thickness or electron density and study this renormalization factor in the experiment. So it actually well coincides with the simple theory. So the degree of manifestation of retardation effects or the strength of plasmon-photon interaction, which renormalize the magnetodispersion, can be controlled by changing the electron density or distance to the backgate. Okay, this is the proof that the dispersion in our experiments remains almost linear. So in the fully screened sample, in the fully screened limit for the first plasma mode, in disk, the wave vector is 3.7 over d. So this is something proportional to the wave vector, and this is frequency. And the plasmon velocity is about 0.8 of the speed velocity in the semiconductor gallium arsenide substrate in our case. So the retardation should be strong, and we actually obtain it. When they go further in higher magnetic fields, we see from the experiment that the magnetodispersion starting to deviate from renormalized cyclotron asymptotics and tends to some kind of horizontal asymptote, which is frequency of some photon mode in the substrate, obviously, because such behavior of magnetodispersion is typical for plasmon-photon hybridization, when the frequency tends to some frequency which does not depend on magnetic field. And now we'll discuss which photon it actually is in the substrate. So our colleague theorist Andreev obtained this simple dispersion equation, which allows to fit the asymptotic in the strong magnetic field and determine more or less exactly the frequency of the photon asymptote, and plotted versus the wave vector for various magnetic fields. So here is the dispersion plots of actual plasmon frequency in zero magnetic field, plasmon-polariton frequency in several magnetic fields, and the red dots is a photonic asymptote. So it's the position of this horizontal asymptote for the samples with various meso diameter, disk diameter in infinite magnetic field. The dashed lines is the light cause.
When usually using the term polariton means some type of dispersion branches out to splits to two modes. So can you here observe the upper branch of your dispersion?
In these experiments, typically it's not easy to observe the upper branch.
But you assume it exists there.
Yes. Okay, so this is dashed lines mark two light cones in the free space and in the semiconductor substrate, and in the zero magnetic field we have ordinary dispersion of screen plasmon with of course accounting some renormalization due to retardation effects, but in infinite magnetic fields the mode is purely photonic and its dispersion more or less closely coincides with the dispersion of TM0 mode in the substrate of propeller thickness. So it's like this. So the result of the first part of my talk is that they actually achieve the regime for screen plasmons where the plasmon velocity is close to the light velocity. So realize a strong plasmon-photon interaction. Shows the renormalization and tunability of renormalization of plasma and cyclotron frequency, and show that plasmons hybridize with the TM0 photonic mode of the substrate. The second part will discuss observation of so-called transverse plasmon-polaritons, and transverse here is a bit marketing term. So, okay, but let's start from the far away, from the waves and 3D plasmons. And 3D plasmons, this equation gives us two cases that modes could be longitudinal, which is determined by the zeros of the electric permittivity and transverse, where the wave vector is perpendicular to the oscillating electric fields. And so in 3D plasmons, usually the modes could be classified as electrostatic modes, like Langmuir waves with no oscillating magnetic fields, and these modes always purely longitudinal. And modes with oscillating magnetic fields, which is commonly called as electrodynamic modes, which is should be at least partially transverse. One of examples of transverse electromagnetic modes in magnetized plasmas is Whisker in atmospheric plasmas. It's kind of circular polarized wave with the wave vector directed over the constant magnetic field, and the dispersion equation of such mode is shown before. And the analog of Whiskers in plasma in metals is helical modes in metals, which is quite similar in dispersion. And of course, there is a question, could we realize some analogy of transverse plasma modes in 2D case, in which it seems that all modes should be purely longitudinal because you cannot provide a wave vector transverse to the 2D electron system. But it was shown by my colleagues. I will just briefly tell you about the experiments that some kind of analogy exists. So if we imagine an infinite two-dimensional electron system, infinite and lateral dimension on the dielectric substrate, and start to measure transmission of this 2D system, yes, there is a non-transparent region in the near the zero frequency. Near the zero frequency, unlike the 2D, unlike the substrate without 2D system, in which the maximum of the transmission should be at zero frequency, and the peak of transmission at the frequency given by this equation, which rather voluntarily was named as a transverse plasma frequency. Okay.
Wait, you just put you don't you just substitute Q with 1 over D.
Yes, kind of. So Q, yes, is inverse thickness of the substrate.
Okay, and
Actually, this resonance adjusts the Fabry-Perot resonance in the substrate, modified by the presence of 2D electron systems on the one side of on the one surface of this Fabry-Perot resonator, and since the 2D electron system.
But why is do you call it transverse manifold just for to sell to sell it?
Ask Vyacheslav Muravyov,
Okay.
who likes such advertising term naming.
Okay.
Okay, but actually, yeah, here is some kind of analogy still with transverse plasma modes in 3D, because in this mode, actually the electrons move coherently in the plane, so you have no variation of 2D electron density within the 2D electron system plane, and some kind of wave vector, yes, is directed normally to the 2D plane. And
I also want to ask you, why do you have so many dots on this figure? For example, for the same frequency, it looks like you have several dots. Is this?
it's not the same frequency. It's a set of very close frequencies because it's. I suppose that it's considered as this work was measured not by me and in quasi-optical setup in the Alexei Shuvaev team in Wien. And in quasi-optics, you have such many interference effects that interfere to measure it exactly, so they prefer to show a lot of experimental points and compare it to the theory. Okay, and what about the fully screened two-dimensional electron system? So a large square of 2D electrons on the substrate with a backgate on the other side. Actually, if the measure the okay, we could not measure transmission in such a system because backgate reflects everything. But we could measure absorption as we typically do. So, and here is a plot of absorption in the real sample with 7 by 7 millimeter square size on a substrate with okay, it's probably the different pictures from different samples. Okay, and here we have 2 peaks, one of which corresponds to the longitudinal mode, and and the other peak corresponds to some other kind of mode, which starts actually we could not actually measure it below 10 gigahertz because they use a waveguide technique of microwave excitation, and they have cutoff frequency of this waveguide. But experiment shows that plasma frequency is very low if it is even exists for this mode. Probably goes from the 0. And then it follows some kind of straight line in magnetic dispersion and tends to some other.
Wait, can I ask also?
Yeah, sure.
On the left panel, you have, for example, for red curve, you have 2 peaks. Are these peaks are shown on the right panel, or is this 2 different peaks?
I suppose that. Let me check it.
Okay. And
Let me check it. 31 gigahertz. Okay. I suppose that these are peaks probably for this one sample.
no, I mean this.
Okay. Yes.
Okay.
But we see some longitudinal mode. Yes, and the mode that we call transverse. Okay, and if we study this theoretical work, calculating the exact equation for the absorption for an infinite 2D electron system with a backgate, and plot the calculated microwave absorption versus frequency and magnetic field, okay, just for some GaAs sample, we will see that this theory gives us that if we study mode of a bass sweep, magnetic field sweeps, we should see something going linearly, following renormalized cyclotron resonance, then tending to a certain photon asymptote, corresponding to a Fabry-Perot resonance in the substrate with the back reflector. So the quarter wavelength is takes place over the thickness of the substrate, and then the upper mode should emerge. Okay. And comparing with our experimental results, we may see that these modes, the observed modes, the red dots, closely follow the maximum of the absorption calculated via Wolters and the Bolot theory.
And the previous slide was about transverse part. Yeah, that's why they don't have up, or they also have longitudinal.
Actually, this theory, this slide, is about infinite sample. But you have no wave vector along the 2D electron system. Actually, unfortunately, in our lab, we cannot prepare an infinite 2D electron system. So we just take some sample with as large as we could. And so it's finite size, 7 by 7 millimeter, and several longitudinal modes is also present. Actually, we have other longitudinal modes, but due to some reasons, the intensities are much lower, so we don't discern them rather clearly to plot their magnetic dispersion. But this mode, plotted by the red dots, are very pronounced and coincides with the theoretical maximum of the microwave absorption for an infinite 2D electron system, and follows the renormalized cyclotron magnetic dispersion and low magnetic fields. Okay, follows this equation, which coincides the equation for renormalization for longitudinal modes, which we discussed in previous part of my talk. Actually, the same equation for renormalization of cyclotron frequency. And at higher magnetic frequency, it tends to first Fabry-Perot resonance in our substrate. And actually, its magnetic dispersion, we take a close look. We could, in case of strong retardation, when they can neglect the unity in the denominator, we could write it in this form. And okay, sorry. This H is wrong and should not be here in the first denominator. Okay, and this is actually some kind of plasma frequency for the 3D electron density with NS divided by the substrate thickness. And this is a square of the speed of light and kind of square of some kind of wave vector, 1 over h. And this is very similar to the dispersion of helicon mode in the normal metals, 3D metals, which dispersion laws is shown here. Okay, so for this reason, we see some analogy between this mode and the transverse mode and 3D plasmas. Of course, it's subject of discussion. Actually, you may not call this transverse one. Yes, no, okay. This is not very important. Okay, so the second part is that we observe a so-called transverse plasmon-polariton in a backgated two-dimensional electron system and show that in small fields its magnetic dispersion is almost linear and follows the renormalized cyclotron frequency. So actually, we may think about this mode as an interaction of cyclotron resonance in infinite 2D electron system, which there is no plasma frequency, as it is infinite, with photon modes, Fabry-Perot modes in the semiconductor substrate. And the strength of this interaction strongly depends on the electron density, actually. So that's it. And the third part of my talk is about the realization of the Purcell for 2D plasmons. I will start with a brief remarks about the plasma resonance line width in 2D electron system. Actually, plasma resonance line width commonly described as a sum of two terms. First is collisional damping due to scattering of the electrons, and it's inversely proportional to the some kind of scattering time, which could coincide with the electron scattering time, but could in some cases diverge from this, from the electron scattering time. But typically for our samples, if we take tau obtained from the mobility DC measurements, it works well for the collision line width. And the second term is radiative line width, because our plasma oscillator radiates in a space. So in infinite system, on the boundary of semi-infinite dielectrics with epsilon 1 and epsilon 2, it's the radiative term is described by this equation, which gamma 0 is this quantity. In a small disk, as it's shown by work of Levitt and Little, when a disk diameter is much less wavelength, it's a wavelength of the radiation in a free space. The radiative term is modified, so the radiative line width now strongly depends on the frequency of the resonance and increases as frequency squared due to this lambda squared. And actually, this radiative term is actually also kind of measure of plasma-photon interaction, because it describes the process of irradiation of a photon. Okay, and one of the most important effects in quantum optics is the Purcell effect, when small quantum oscillator is placed in a resonator in a cavity with a high Q. The cavity field leads to a strong increase of radiative decay rate if our oscillator is tuned to the resonator, and a strong suppression of radiative decay rate when it's detuned from the cavity mode. It's widely used in quantum optics. In classical systems also, the Purcell effect should be was realized for point-like detects in photonic crystals working as meta-atoms. Yes, but typically the Purcell effect was studied either for quantum oscillators or for classical but point-like oscillator. And there is lack of realization of the Purcell effect for both classical system like 2D plasmon and very extended system like a 2D plasmon and 2D electron system. And actually the realization of the Purcell effect for the 2D plasmons allows us to control the radiative line width, which is important for using the plasmons in devices like plasmonic detectors or plasmonic modulators and so on. So now we will show you some experiments on the samples of disks of small diameter, 0.8 millimeter, on a semiconductor substrate. And actually, our sample always has a substrate. And this substrate works as a Fabry-Perot resonator. So let's use it as a kind of resonator and try to demonstrate the effect of resonator on the radiative line width of the plasma. So here we show magneto dispersion of the fundamental plasma mode. We plot its dispersion of the upper bulk magnetoplasma mode in the disk. Okay, I will not discuss it in a great detail, actually, but now we will start to measure the line width at this point, this point, this point, and plot the line width versus frequency of the resonance. And we will obtain this plot. So this is the experimental points demonstrating the drastic increase of radiative line width on a certain frequency, about 67 GHz. And the line is a simple theory which predicts the square dependence of line width versus frequency for the D plasma. And in this region, we will see that experimentally measured line width is less than theoretically predicted. And in this region, the experimentally measured line width is much higher than theoretically predicted one. And for this region, I should say that here, this approximation is lost its validity because the condition that the diameter is much less wavelength is not valid here, actually. So it works well in this region, below about 60 GHz. We see that this frequency where the radiative line width of the plasma resonance strongly increased actually coincides with the first Fabry-Perot resonance in the semiconductor substrate, as should be expected. Actually, if they measure it for the different substrate thickness, we will see the second peak, which is also in good coincidence with the position of the Fabry-Perot resonances in the substrate. And actually, sorry for not very good picture quality. Actually, if we change the back reflector to an absorber, actually prepare the sample without back reflector and mount it on the microwave absorber, we will see that this peak is almost fully disappears. And this is a sign that the origin of this peak is caused by the presence of the reflecting backgate, which provides us Fabry-Perot resonance in the substrate, acting as a resonator. And okay, and also we may try to calculate simple theory. So for extended absorber on a substrate, in this work, theory in this work was done by mostly by Mikhail Glazov of Biov Institute. Actually, was obtained this equation for the Purcell factor, which is 1 plus real part of the total reflection of the substrate, and we could calculate reflectance and the Purcell factor, and it is okay. It wasn't plotted on this picture, but actually it shows, yes, that near this frequency we should observe the increase in the radiative line width. Actually, the maximum value of such a Purcell factor when our system is on top of the resonator is 2. And this is the observe the increase in radiative line width at about 1.7, not ideal 2, but something close. I think for the taking into account that our sample is not infinite, it's good coincidence with such simple estimation. So, and actually we demonstrate that the substrate acts as a resonator and could tune and modify the radiative line width of the plasmon resonance. And actually, if we place 2D system not on top of the Fabry-Perot resonator, but something in the middle, this increase could be even greater than 2. Okay, so I suppose that's all for today. Thank you very much for your attention. Question, please.
Okay, do you have, let's first start from Zoom. Misha, do you have question? Or if not, okay, do you have question? More? I have, but no. Okay. So when you were talking about retardation parameter, in theory, if I remember correctly from my conversation with Vladimir Alexandrovich Volkov and with Andreev about this, they have a retardation parameter like 2 pi or 4 pi times conductivity of two-dimensional system divided by speed of light. Yes. So and when this parameter is large, so when conductivity of two-dimensional system is which have dimensions of velocity, when it's larger than speed of light, then something new may happen. So whether this A or when A is close to 1, as far as I understand, what is the typical value for this parameter conductivity divided by speed of light, conductivity of two-dimensional system divided by speed?
Okay, this is 2 different parameters. Both of them,
yes, I understand,
are very important. Yes, but this kind of retardation parameter contains also the wave vector.
Yes.
But typically, in such when the retardation parameter A is about unity, 4p sigma over speed of light typically also tends to unity or exceeded in common samples.
Okay. Let's thank our speaker again, and we, for all our speakers, we present science of our public center. Thank you.
Thank you.
So, the end.
Сегодня никто не хочет